Thank you so much for being here for our Science Circle lecture today. I welcome you on behalf of the German Center for Research and Innovation. My name is Adishri Jamkhedkar and I'm the program manager of the center in India. Thank you for joining us from wherever, from India and Germany, or from other places that you are joining us today. And this is our first Science Circle lecture of the year. And we will speak about the topic of astrophysics and address it with the title, Why is the Universe Not Empty? We have our guest here, Professor Matthias Bartelmann from the University of Heidelberg. Welcome, Professor Bartelmann. I have my colleagues here joining with us today. So Ms. Ramneet Mehta and Ms. Karma Behal, that's our team here today, helping in the background. Unfortunately, Dr. Bartelmann is not able to join with his video, but he's present with his audio here completely. That's working fine for him. But I'm sure this will still be an interesting talk and we are able to have an interactive session. I would just like to introduce the German Center for Research and Innovation shortly before we move ahead for those who do not know it. The DWIH, or the German Center for Research and Innovation, is a network of German research institutions, funding bodies, research-based companies, and 5 such centers exist across the world. In India, we act as a gateway for Germany to access India's research and innovation ecosystem, and also the other way around for India towards Germany. We offer a platform for enhancing research cooperation and offer networking possibilities, exchange cooperation possibilities for academic communities and researchers and also innovators. Our activities focus on topical issues in science and humanities, and we cover a lot of fundamental as well as applied research. Now, with this introduction, I'm going to hand over to our guest here today, guest and colleague, Mr. Philipp von Ritter, who's the science counselor and head of the science and technology section at the Embassy of Federal Republic of Germany in New Delhi. He's here to give us a short welcome address. Welcome, Philipp, and thanks so much for joining us. Over to you.
Adishri, thank you. Also from me, a very warm welcome to everybody. Science Circle lecture, which is, as was said, hosted by the DWIH, German Center for Research and Innovation, Uni Heidelberg, and also the German Embassy of Science Counselor. I'm really pleased to be here. Have today a topic which fundamental nature. So really very, very fundamental. And I think it's good that we have a Science Circle lecture and a discussion on the topic of fundamental research in a time where we have so many discussions on applications to battle the pandemic. And I think it's really very important to always strengthen fundamental research also in this situation. And that is for several reasons. I mean, for once, I think it's obvious that research gives us a toolbox which radically increases then our options for practical solutions for urgent challenges. And you can see it very clearly with the messenger RNA vaccines that have been deployed so quickly, and also with the CRISPR-based Feluda rapid test that has been developed here in India. Also because I think the fundamental research really embodies that freedom of research, where you, in a way, the researcher follows their inclination and their curiosity rather than a government or state or society given list of priorities and missions and strategies. So really embodies this idea of academic freedom to the fullest. And that is a very important reminder and inspiration of this importance of academic freedom. It's also we have a topic of fundamental research, because Indo-German research is extremely strong in fundamental research. Indo-German cooperation there is very strong, which is, of course, because both India and Germany are the home countries to really brilliant researchers in the fundamental sciences also. There are countless consortia, co-publications. There are so many joint calls also in different disciplines. And we also have cooperation in large-scale mega science projects. For instance, in the FAIR particle accelerator in Darmstadt, where in a way the conditions of moments that we will probably hear about in a moment are recreated in a huge particle accelerator in which India, to which India is a really important contributor, both in financial terms, but also in terms of equipment. Brilliant physicists. And the fourth reason, perhaps, that comes to my mind, we speak about fundamental sciences, because I have the impression that fundamental research is something that, despite its abstraction and sophistication, is able to, it has a fascinating potential to touch us all, because it speaks in certain ways about our deepest questions, hopes, and worries of us and of our existence. And I think tonight's topic is a powerful example for this. Why is it, are we here? Is it trivial that we are here? Huge coincidence, or is it? Yeah, where does it all come from? All these questions, they came suddenly to me after I read the topic of tonight's lecture. And we are really extremely lucky to have, for tonight's lecture, a renowned expert in the field, and one who speaks also not only with authority on this topic, but also with a lot of passion, and I've heard with a lot of wit. And this is you, Professor Bartelmann. Professor Bartelmann, he studied physics in Munich and has done extensive research in Munich, Harvard, and Heidelberg, among other places. And he has been professor of theoretical astrophysics at Heidelberg University since 2003, where he's also the head of the Institute for Theoretical Physics. Research interests concern the formation and evolution of cosmic structures, which he studies with theoretical methods. He has been Dean and Vice Dean of the Department of Physics and Astronomy, a board member of the German Physical Society, and the chairman of the Committee for Research and Strategy at Heidelberg University. And in addition to his extensive research, Professor Bartelmann is known for his insightful and approachable lectures on physics to also a wider non-expert public. He regularly addresses the role of physicists in tackling global challenges, including energy efficiency, climate change, scarcity of resources, and also wider issues like moral principles for scientists, role of humility in scientific research, and also the link between science and happiness. The latter he discussed with the Dalai Lama some years ago in Heidelberg. Professor Bartelmann, thanks for being with us. It's a great pleasure to have you speak to us tonight, and I won't stand between the audience, between you and the discussion anymore. The floor is yours.
Thank you very, very much for this kind introduction, and also for the great honor to be able to speak to you this evening about such a topic which is apparently so remote. I'm very grateful for the opportunity that I have to give this lecture. And I should say that the technical problem that makes me invisible to you is not at all the fault of the wonderful team at the DWIH, but entirely my fault. I have just not been able to connect in such a way that my video camera would be linked. Anyway, I think you can hear me. If you can't, please let me know. And I think it's way more important that you can see the slides rather than myself. So, Why is the universe not empty? This seems to be an entirely trivial question. But what I would like to explain to you in this lecture this evening is that this very simple question leads us directly to the frontiers of science in several areas of physics. So if you have a look at the next slide, let me introduce some of the cosmic structures that I'm talking about, some of the things that we see in the universe if we look around. So here you see a model or an illustration of the solar system, which is our immediate cosmic neighborhood. So in the center you see the sun in what may be an unfamiliar representation. And then to the right of it, you see the innermost planets, Mercury, Venus, Earth with the Moon and Mars. And to the left, you see the outer giant gas planets, Jupiter, Saturn, Uranus, and Neptune. And Pluto there in the distance. So this is our immediate cosmic environment. Now, if we go a little bit to a little bit larger scale on the next slide, you see an elliptical image. And during the lecture, you will see many more of these elliptical images, and each of them is going to be a map of the entire sky. So what you see here is a map of the full sky as you would see it if you could see the full sky with your bare eyes. And along the equatorial line of this ellipse, right, along the long axis of this ellipse, you see the plane of the Milky Way galaxy. The Milky Way galaxy is our stellar system. It's the stellar system that we are embedded in. And apart from the sun, the Milky Way consists of approximately 100 billion stars. And it's arranged, these stars are arranged in a rather thin plane, which you see here from the side, of course, because we sit in that plane. And in the middle of the image, there is the center of the Milky Way, which is enshrouded and partly covered by dust clouds, which you see as black features in front of the light from the center of the Milky Way. And if we could see this host galaxy from above, as it is shown in the next slide, it would roughly look like this. It would look like a loosely wound spiral. And with our sun, we occupy a place rather remote from the center of that galaxy, approximately 25,000 light years from the center of the galaxy, in one of these spiral arms. So why I'm showing you this? I'm showing you this because this illustrates our local environment where we find ourselves in the universe. We are part of the solar system. The solar system itself is part of a galaxy, right? A huge system of stars. But now if we change the perspective even more, right? If we even go to larger scales than that, on the next slide, you see that galaxies assemble in groups and clusters. You see one of these galaxy clusters here. It's a galaxy cluster that is visible in the constellation of Hercules. And almost all of what you see on this image are galaxies. And there are spiral galaxies, there are elliptical galaxies. If you look closely, you see that some of these galaxies are even merging, right? They meet and they interact, they build new galaxies, and so on. And if we, on the next slide, if we widen the perspective even further, you see again a picture of the full sky. You see again a picture centered on the plane of the Milky Way. But now you see the entire sky covered with dots. And this is a real image, right? This is an image of real data taken in the course of the so-called 2 micronal skies away. And it's a survey of the entire sky that was taken in the near infrared, right? A 2 micrometer wavelength. So there's a wavelength larger, wavelength of electromagnetic radiation, wavelength of light that we see, larger than what our eyes are sensitive to. And in this range of wavelengths, we can look past or through the dust clouds into the center of the Milky Way that you now see shining in the center of the image. Now you also see that the entire sky is densely covered with dots. And these dots, each of these dots, is a galaxy on its own, a galaxy like our Milky Way, consisting of billions or tens of billions of stars. And the color of each of these dots indicates the rough distance, or the approximate distance to this galaxy. And this is still our cosmic neighborhood. You see illustrated here is still close to us. Right? This is our environment. This is what we see. This is an image of the structures that we see surrounding ourselves in our cosmological neighborhood. And of course, the immediate question that may arise if you look at this image is, where did the structure come from that you see on this image? And you see that galaxies do not at all cover this ellipse in a random way, but they group and they form filaments, form a network-like structure. And of course, as astrophysicists or as cosmologists, we want to understand, where did these structures come from that we see in our environment, in the universe? So where did the sun come from that we live from? Where did the planets come from that we live that we live on? And how did all of this form? Now let us have yet another look at the full sky with a completely different eye, an eye that you see on the next slide. This is an antenna. This is, if you want, an eye that extends the range of electromagnetic wavelengths, of the wavelengths of light that we are able to perceive, into the radio waves. In fact, into the range of wavelengths of approximately a centimeter. So these are relatively long waves in comparison to what our eyes are sensitive to. And this is an ancient antenna. Nowadays we would use different instruments for doing what I'm going to describe. But this antenna was the first to see what I'm now going to show you. Because if you point this antenna to every point in the sky, and as the Earth is rotating, also the point on the sky that the antenna looks at is going to move across the sky. So it is possible to map the entire sky with this antenna, even though it seems to be very large and rigid there. So if you scan all the points on the sky with this antenna, then you see one of the most fascinating images that cosmology has to show. You see this on the next slide. You see, this is one of the most fascinating pictures. Now I need you to go one step back. Thank you. This is one of the most fascinating pictures that cosmology has, because it shows that if you look at the entire sky with an eye like this antenna that is sensitive to wavelengths of approximately a centimeter, then you see that the intensity of the radiation that you then receive is almost the same everywhere on the sky. And you can characterize the intensity of this radiation by a temperature. And the temperature turns out to be approximately 3 degrees above the absolute 0 point of temperature. So this is approximately a temperature of minus 270 degrees centigrade. And now you can subtract the mean value of this map. Right? And now you see, if you move one slide ahead, that if you remove this mean intensity, if you remove this mean temperature of 2.7 or approximately 3 degrees Kelvin from this map, then you see tiny little temperature fluctuations. So what you see encoded in this color map here is the temperature fluctuation above and below the mean value of about 3 kelvins. So the blue spots are a little bit cooler than 3 kelvins, and red dots are a bit hotter or a bit warmer. And between cool and warm, there's a difference of approximately 100,000th of a degree. These are tiny little temperature fluctuations. And we know from rather elementary physical considerations that this radiation was released when the universe was approximately 400,000 years old. So in this red map, which I told you is one of the most fascinating maps that we have in cosmology, you see the leftover heat radiation from the warm and the hot beginning of the universe. And very quickly after the beginning of the universe, just 400,000 years later, we see these temperature fluctuations in the very early universe. And I showed you the structures that we see nowadays in our environment in the universe. So on the next slide, you see these two instances of time juxtaposed to each other. You see the initial state of the structures in the universe about 400,000 years after the Big Bang in the top left of this slide. And in the bottom right of the slide, you see the structures that surround us nowadays, about 14 billion years after the Big Bang, after the origin of the universe. And now the very simple question, of course, arises: can we understand how we get from the observed initial state of structures in the universe to the top left in this slide to the equally observed late and evolved state of structures in the universe? And the very simple and straightforward answer is no, we cannot. No, we cannot understand how we go from the upper left on this slide to the lower right, unless we assume that by far the most of the matter in the universe does not at all interact with light, and therefore is of an unknown form of matter, which we call dark matter, and of which we know how much there is in the universe, which we also know how it is distributed in the universe, but of which we do not know what it consists of. So if we have a look at the next slide, this is a very rough display of what the universe is composed of. And the very little sector, the light blue sector on this slide, that illustrates the kind of matter that we know of and that we are used to. These are the atoms. This is the kind of matter that we consist of, for example, that the Earth consists of, and that everything visible consists of, that I showed you in the previous slides. And then we know that just 4.6% of the energy density in the universe is composed of these atoms, and about 23% of the complete energy density in the universe are composed of what we call dark matter, and where we do not know what it consists of. And the very large rest of approximately 72% consists of dark energy that I would not like to speak about this evening. I would just like to focus on the ordinary matter, the atoms, and the dark matter that I try to illustrate to you. But now let us focus on the atoms. Right? So the conclusion of what I said so far is that we see ourselves surrounded by very rich structures in our cosmic neighborhood. And we can observe these structures, we can quantify them. And we also see a state of the universe approximately 400,000 years after the Big Bang, where we can also see already structures that are reflected by the temperature fluctuations in the leftover heat radiation from the origin of the universe. And if you want to understand developed into the structures that we see today, then we already have to recognize that we can only understand that if we admit that by far most of the matter in the universe is dark and does not interact with light. And we do not know what this dark matter is composed of. But let me now come to the atoms, which apparently are the type of matter that we understand very well. So let us have a look at the next slide, where you see an atom. It's a display, not to scale, it's a display of an atom. If you look closely, you see that this is a helium atom, which you can recognize because it has a nucleus in the center that is composed of 4 what we call nucleons, the neutrons and the protons. And the big red spot, or the 2 big red spots in the center, are called the protons, and the 2 gray spots in the center are the neutrons. Both of them, the protons and the neutrons, are structured. They consist of what we call quarks, but I don't go any further into any more details here. And you see this nucleus composed of 2 protons and 2 neutrons surrounded by electrons, 2 electrons in this case. And what is not to scale in this image is that the electrons move around this nucleus at a distance that is very, very much larger than the diameter of the nucleus itself is. All right, so this reflects the particles that the atoms consist of, that we know of, and that we know that the ordinary matter is composed of, that we are all composed of. So if you click once more, if you go, you see a map of the. Well, could you go back one slide, please? And now click once more. No, in the other direction. Okay, well, there should appear something little there, but this doesn't matter. All right, what I wanted to say is that we speak of baryons, such as the proton and the neutron, that each consist of 3 quarks. And the quarks and the electrons, or as we say, the quarks and the leptons, of which the electron is an example, together form what we call the standard model of elementary particles. You see a lot of detail on this slide, but what I would like you to focus on is just the leftmost column on this diagram. And in purple, you see outlined 2 types of quark, up, down, and the up, the up quark and the down quark. And underneath, you see outlined in green the so-called leptons, the electron and the electron neutrino. These form what we call a family of elementary particles. And the standard model of elementary particle has 3 of these families. Then you see a red column. These are the particles that mediate the interactions between the particles, the electromagnetic interaction, the strong and the weak interaction. And then there's the Higgs particle that gives a subclass of elementary particles its mass. I'm not showing this to you because I want you to memorize all of that. I'm showing this because I would like to make the following point. There is known matter in the universe, right? These are the ordinary atoms. And we can decompose these atoms into two types of particles, the quarks and the leptons. And what comes out from that is a very well-ordered standard model of elementary particles. All right, if we move on to the next slide. Here it comes. Okay. If we move on, yeah, could you switch to the next slide, please? Thank you. Yes, this is it. All right. But now I need to tell you a brief story about theoretical physics. So what you see in this image to the left is the famous theoretical physicist Paul Dirac, who in the 1920s and 1930s was one of the eminent theoretical physicists who designed quantum mechanics. So the theory of subatomic particles. And what Dirac found by purely theoretical considerations was that he could set up a theory for electrons that was in agreement with Einstein's theory of special relativity, only if he assumed that each particle has an antiparticle. Now, to the complete world of particle physics, there's a mirror world of antiparticles, which are identical to the elementary particles, except for one thing, namely except for the charge. So Dirac found that he can describe an object as the electron in agreement with Einstein's special relativity only if to each particle of the world, to each particle in the atomic world, there exists an antiparticle which has the opposite charge. So here you see again the quarks and the leptons, right? You see the three families, which are the three columns. The leftmost are the quarks and the leptons that we already met, right? The up quark, the down quark, the electron, and the electron neutrino. You see the three families. And you see the mirror world of antimatter. Now this, you might say, is a completely theoretical perception, right? It's a theoretical thought that sprang up in Dirac's mind, but very shortly thereafter, the anti-electron was found. It was experimentally discovered that there is a particle, an elementary particle, which has the exact same properties as the electron, same mass, the same spin, but opposite charge, right? Positively charged instead of negatively like the electron is. So in other words, this completely theoretical perception of Dirac's was very shortly thereafter verified by experiment. Now this is very interesting. This is very interesting because what happens if a particle such as the electron meets its antiparticle, such as which is the positron, is that the two annihilate, right? The two particles meet, the particle and the antiparticle, and they meet and form electromagnetic radiation, gamma radiation, and they disappear. Now this is very interesting from a cosmological perspective. If you move on to the next slide, we can go back to this overwhelming picture of cosmology, right? Our purple ellipse, of which I said this is a map of the leftover heat radiation from the Big Bang, from the origin of the universe, which has by now cooled down, of course. But all the photons, right, all the light particles that formed in the hot beginning of the universe, they are still around. So how many are there? If you move on to the next slide, I want to illustrate that we can in fact find out, first of all, that this radiation, which irradiates us from everywhere on the sky in the same intensity, is indeed heat radiation. And since it is heat radiation, we know exactly how many photons there are. So there was an instrument which was on board the COBE satellite that you see as an illustration there. The instrument was called the FIRAS instrument. And this instrument mapped between 1990 and 1992 the electromagnetic spectrum of that radiation. And this spectrum you see on the next slide. See, this is the spectrum, and the measured data points are those in yellow, and attached to these data points are error bars, but these error bars are magnified by a factor of 400 in comparison to what is shown on usual plots. And they are magnified by that much because the error bars are so small, and they are so small that this curve of heat radiation, the so-called Planck curve, is the best measured curve of heat radiation, including all laboratory experiments on Earth. And you see a red curve running through all the data points. And this red curve is the theoretical expectation for heat radiation. And this curve has only one free parameter, which is the temperature. And by making the red curve run through all the yellow points, we can measure the temperature very well. And this turns out to be these 2.7, in fact 2.715 degrees Kelvin, or 2.715 degrees above the absolute 0 point that I mentioned earlier on. But if we know that this leftover radiation from the Big Bang is in fact heat radiation, and if we know what the temperature of that heat radiation is, which we can measure, see, I'm showing you lots of measurements here, I'm not speculating. So if we can measure this curve, then we know how many photons there are in the universe. And we know that in each cubic centimeter of the universe surrounding us, there are more than 400 of the photons that are left over from the hot origin of the universe. Now we can do a similar experiment with the ordinary matter, with the baryons that surround us. If you switch to the next slide, I'm illustrating what happens to these baryons. I mentioned that baryons are particles that are composed of 3 quarks. And the most prominent examples of these are the proton and the neutron. And what you see here in the 2 identical halves, the top half and the bottom half of this slide to the left, is that a neutron meets and the 2 particles together form what is called the deuterium nucleus. It's called heavy water or heavy hydrogen. And then 2 of these deuterium nuclei meet and they form helium. And this is one of the most elementary processes that happen to those baryons in the very early universe. In fact, they happen very early. They happen within approximately 3 minutes, after about 5 minutes, after the universe is about 5 minutes old. So in this process, protons and neutrons are being turned into helium. And if you switch to the next slide, or if you click once more, we can model very well how these neutrons and protons are fused to make helium. So on this diagram, which is a little bit complicated, on this diagram you see, first of all, along the horizontal axis, the cosmic time in seconds. You see it starts with 10 seconds to the left, it's 10 seconds after the Big Bang, and it ends at 10 to the 4 seconds after the Big Bang, which is approximately 2.5 hours after the Big Bang. And you see a yellow line on the top. And you see a light blue curve below that. These are the neutrons. And then suddenly, approximately 200 seconds after the Big Bang, the neutron curve drops rapidly. And the hydrogen curve has a little dip. And this is the moment when suddenly nuclear fusion begins and turns much of the, or turns a good fraction of the original protons and neutrons into helium. And this process, which took a few minutes, was so efficient that of each kilogram of hydrogen in the early universe, approximately 240 grams were turned into helium. And this number, right, 240 grams out of a kilogram that we now find in helium, can be used to calculate, can be used to find out how many baryons there are in the universe. And it turns out, and this is very, very surprising, if you compare the number of photons that we can measure in the universe to the number of baryons that we can equally measure in the universe, it turns out that for each baryon that we now have in the universe, there is approximately 1 billion photons. There's 1 billion photons for each baryon in the universe. How can this be? I told you that we have for each particle in the world, we expect an antiparticle in the mirror world. And we would expect that the particles and the antiparticles should have been produced in the very early universe in equal amounts. But if this would have been the case, then there would be no matter, no baryons left at all, right? Because all the baryons would have met the antibaryons and would have disappeared into radiation. We see a lot of radiation, right? We see 400 photons in each cubic centimeter of the universe. And we know that for each billion of these photons, we have a single baryon left. And this tells you that there must have been a very slight surplus of baryons in the very early universe, such that if the baryons and once the baryons and the antibaryons met, almost all of the baryons disappeared and annihilated with the antiparticles, except for approximately 1 baryon in 1 billion. And so out of 1 billion baryons plus 1, 1 billion baryons met the antibaryons and disappeared and formed photons, and 1 baryon was left. This is a most surprising observation, right? And it shows you that since we know that there must be matter and antimatter in the universe, we would expect that the matter and the antimatter would have been produced in equal amounts, but it wasn't. It was produced in almost equal amounts, so that for each billion of antiparticles, 1 billion plus 1 particles were formed. And the billion antiparticles annihilated the billion particles. And 1 particle, 1 baryon, for example, was left. Now, this is a most interesting and most astonishing finding. There must have been a slight asymmetry between the baryons and the antibaryons, between the particles and the antiparticles in the universe. If you go to the next slide, you see a famous person who in 1967 first thought about the possible origin for this very small asymmetry between the particles and the antiparticles. And the person you see there is the eminent Soviet physicist Andrei Saharaf, and according to him, or by his name, these conditions that I'm now going to speak about are called the Saharaf conditions. And as I said, they are known since 1967. So Saharaf discovered that there are 3 necessary conditions for this very small asymmetry between the baryons and the antibaryons to have been formed, namely, that it must be possible, obviously, to convert baryons into something else. That's condition number one. Condition number two is that once you have destroyed a baryon, you must not be able to recreate it. And this means that physical laws must be slightly different for matter and for antimatter. There must be a slight asymmetry of physical law, of physical laws that apply to matter and those that apply to antimatter. And condition number three, the very early universe cannot have been in thermal equilibrium. All right, let me briefly go through the main arguments of my talk again. I began with showing you cosmic structures, right, such as the solar system, the galaxy, groups of galaxies, and the whole structure that surrounds our position in the universe. And then I switched to the very early universe, looking at electromagnetic radiation with a centimeter wavelength, showing you the heat radiation that is left over from the early universe, and showing you that even at that time, when this radiation was released 400,000 years after the Big Bang, there were already in the universe. And if we ask, do we understand how these very early structures in the universe turned into the structures that we now see in our surroundings, the answer is a very clear no. We do not understand how the early state of the universe turned into its evolved late state, unless we assume that by far most of the matter is dark matter, does not interact with light. And we know how much dark matter there is in the universe. We know how it is distributed in space, but we do not know what it consists of. Now, putting the dark matter aside, we spoke about the ordinary matter, the ordinary atoms that we are all composed of. Atoms that consist of a nucleus and electrons, an electronic hull around these nuclei. And the nuclei consists of baryons. And the standard model of particle physics says that there are only very few really elementary particles, right? There are the quarks and the leptons. And from the quarks and the leptons, you can assemble all the matter, all the ordinary matter that we know of. But we also know that for each particle in the world of elementary particles, there must be an antiparticle in the mirror world that Paul Dirac, first of all, discovered by pure thought, and that was very shortly later confirmed by experiment. But then we have to ask, if we know that there is matter left in the universe but no antimatter, what's the ratio between the matter that survived and the overall matter that very early in the universe must have been formed? You find that for each billion of antiparticles that have been formed in the early universe, there must have been a billion plus one particle, such that a very tiny part of the original matter and antimatter could survive. So there must have been an asymmetry between the formation of antimatter and matter, and the Saharaf conditions that we know of since 1967. This asymmetry could have arisen. But now, of course, the question is, in what we call our standard model of particle physics, do we understand how these Saharaf conditions could be realized? And the answer is yes, we do. Right? We know ways of arranging the Saharaf conditions in the standard model of particle physics. But if you ask further, does the standard model of particle physics explain the amount of asymmetry between baryons and antibaryons, between matter and antimatter? Then the answer is a clear no. So far, so as of yet, we do not understand how the Saharaf conditions, in the amount necessary to explain the observations in the universe, could have been arranged. And so what I wanted to tell you in the course of this lecture was, first of all, what do we see in the universe surrounding us? And if we look at what we see surrounding us, and if we look back in time, do we understand how things formed? And what we have to conclude is that even a question as simple as, why is the universe not empty, takes us immediately to the limits of, or to the bound, of fundamental research in physics. So at this point I stop. Thank you very much for your attention. Sorry again for not being visible, but I think the much more important part of the lecture has been visible. Thank you very much for showing the slides also.
Thanks a lot, Professor Bartelmann. Thank you so much for your talk and giving us insights into the topic. We have some time for taking questions now. So if anyone from the audience has questions to ask, I request you to type them in the chat option or the Q&A option that you also see here. We will give those questions to Professor Bartelmann. He will be able to answer them via audio. Are there any questions?
I hope I will be able to answer them.
Perhaps may I start, Adi Schrieb, with one question?
Please, yes. Go ahead, Philip.
So thank you very much. This was really fantastic, and yeah, in a way, it was. I mean, it would have been great to see you, but it was also great to be able to focus on your slides and on the images. So really, thank you so much, Professor. And I have one question, which may be really stupid, but so why can we not detect this this dark matter? You said that it's scientifically we can prove that it exists, and there should be 400 per, I don't remember what size, but is it right that we can't detect it, and why is that so?
Yeah, it's not at all a stupid question. So the question, as I understand it, is why can we not detect the substance that the dark matter is made of? And the reason is that these particles must interact only very weakly. So the strongest interaction that we know of is the electromagnetic is the electromagnetic interaction. This is the interaction that keeps the particles of our bodies together, for example. And very much of what we know about the world of elementary particles comes about because particles interact electromagnetically or with a strong interaction. But we know that this cannot be the case for the dark matter, right? It cannot participate in the strong interaction because then nucleosynthesis, so the formation of elements, would proceed in a different way. And it cannot interact electromagnetically because then the temperature fluctuations in the leftover heat radiation from the Big Bang would show much larger temperature fluctuations, a factor of 100 larger temperature fluctuations than it does. So we know that it does not participate in the electromagnetic nor in the strong interaction. And this means that whatever dark matter particles do in detectors, for example, that we put into their way is very, very, very little. And so far we have not been able to find any clear signal that could be attributed to dark matter particles. So we, in fact, we don't even know of, or we have become more and more doubtful that dark matter particles are in fact elementary particles, which we really don't know. Does that answer your question?
Yes, thank you.
All right, now I'm going to read from the chat column. And the first question that I'm reading is, can matter, antimatter, and anomality be explained by considering the antimatter's energy getting distributed in entire space, with each phase space quanta getting some some amount of energy. So as I understand the question, it means, could it be that the antimatter is just homogeneously spread around in space? Is that the right interpretation? Well, if it is, then we know that the matter and the antimatter, matter particles and antimatter particles, have the same mass. And this means that they are subject to gravity in exactly the same amount as matter is. So this means that the antimatter must form cosmic structures in the same way as matter does. And this implies that antimatter cannot be homogeneously distributed if matter is not. And I hope this answers the question, and I hope I understood it correctly. So let me come to the next question that I see in the chat column. This is, what is antimatter? And the answer is that to each, or the antiparticle to each matter particle has the same properties as the particle, but the opposite electric charge. So it's matter that was a form of matter that, so to speak, looks exactly like the matter, but has the opposite charge. The positron, as the antiparticle of the electron, has the same mass, the same spin as the electron, but opposite charge. And the anti-up quark has the same mass as the up quark, and the same spin, and so on, but the opposite charge, and so on. And so antimatter is an oppositely charged form of matter. This is the rather straightforward explanation. All right, then I'm coming to the next question that I read in the chat column, and the question is, you mentioned an incredible amount of photons. What form do they take on around us? Are they just pure energy or light, or how do they influence us? It's also a very good question. I mentioned that there are 400 leftover photons from the Big Bang in each cubic centimeter in our cosmic neighborhood. And they are photons of shortwave radio light. So, for example, the microwaves that you produce in a microwave oven are of approximately the same sort or as those photons that we see in the universe. And it's true, they are just pure energy or light, right? They are just ordinary electromagnetic radiation that reaches us still from the very early times of the universe. Now, if you ask how they influence us, even though they store an enormous amount of energy, this energy is very, very homogeneously distributed. And the energy of each individual of these photons is very, very small. So they correspond to a temperature which is now on the order of to an energy. Well, numbers wouldn't tell much, but each individual of these photons carries a very, very small amount of energy. So effectively, they do not at all influence us, but they are all around. Then I'm going to read the next question in the chat column. Is it possible that there are isolated galaxies made up of only antimatter? Yes, there is in fact a possibility like that. The only caveat that would apply to that is that it would have to be a really, really isolated galaxy, because any kind of interaction with its surroundings made of ordinary matter would lead to an enormous outburst of gamma radiation, right, of very highly energetic electromagnetic radiation. And so we do not really believe that there are isolated galaxies made up only of antimatter, because we never have seen an outbreak of gamma rays like that. But let me first come to the question that follows that. Sir, can I work under you as a research intern? Turn to the Heidelberg Center for South Asia in New Delhi, and they have a very well established infrastructure for connecting German universities and Indian universities. All right, now I come to the question. Can there be an absolute field existing and perturbations in that absolute field be the source of materialistic particles? Well, yeah, that's the picture of quantum field theory, which you are describing there. Right? We believe that all the elementary particles that we see are in fact excitation states or perturbations of quantum fields that pervade space. So in a sense, yes, not only can there be, but there are fields existing, quantum fields, whose excitation states or perturbations are in fact the materialistic particles. All right, and now I stop. Sorry for the questions that I could not answer.
Yeah, we're sorry for not being able to take all the questions here. We're a little bit restricted by time. But thank you so much for answering these questions. Thank you so much for the lecture. For those of the participants who wish to find out more about the University of Heidelberg, we will shortly put a link to their office, which is in New Delhi. Feel free to go over to that website and see what options do you have for research there, and connect with the representatives there. They are a very strong supporter in our entire network. Right, so that's the link in the chat box right now. Yeah, once again, thank you so much everybody for joining in. And for those of you are interested in research activities between India and Germany, we have a very big event coming up mid of March, which is the Indo-German Forum on, unfortunately, not anything related to astrophysics, but on cities and climate, where we would have about 35 speakers, 25, 30 institutions who will be who will be available to present their research projects related to the topic of cities and climate change. So do drop in, take a look at this website, and there you would also be able to meet representatives of several German universities and see what are the scopes there for your research. All right, so on this note, I would like to thank once again everybody, and wish you a nice day and a nice evening for wherever you're joining in.
Thank you very much for the wonderful opportunity and for your great support and for your attention and patience. Thank you very much.
Bye-bye. Thank you so much.
Bye-bye.